Okay, so we are recording. Okay, we went through the first two questions. So here comes question number 3. There we go. All right. Okay, it is 32, so I'm getting started here. All right, so getting back to this question, so let's read the question again now that we have spotted some of the problems. Find out which cases it will fail and fix it. Okay, so under what conditions do you think it's going to fix? So you have to kind of keep in mind how the assembly code is actually written, because I am not using the stack, and in this case I am explicitly saying the maximum length is only 32. Okay, so you don't have to worry about, oh, but what if the maximum length cannot be stored in a byte? Okay, we know it can be stored in a byte because it is defined exactly the way it is. We know that string 1 has 32 bytes and string 2 has 32 bytes, but what we cannot control, yes?
Are you recording this?
Am I
recording this?
You didn't pay attention when I said, it is being recorded.
Okay.
Yes, I am recording this. In fact, I double-checked twice, so I triple-checked.
Okay. Thank you.
Okay, so it is being recorded, the audio is good, and it is being saved. All right. So getting back to here. Okay. All right. So, but the question is asking, when do you think the problem is going to happen? So let me go back to here. Okay, note that some problems may not show up due to the addresses of string 1 and string 2, or the values of extra bytes after the null character. Okay, so let's see what else we can see from this code that can potentially be a problem. Okay, in your string homework, the last homework that you did, I think some people might have, step on this one, is to use a compare long instead of a compare byte when you're only supposed to be comparing bytes. In this case, we don't really quite have that problem in the loop. Okay. All right. So what I'll do is I'm going to comment, this code here. Okay. So this is the beginning of a while, and the while is basically saying while DL is non-zero, do the following. So I'm going to use # here just to make sure that it is just commenting. Okay. And inside the loop, this is what we are doing. This is just a comparison. So that means this is not the only condition to stay in the loop. We have another condition to stay in the loop. If DL is 0, we exit the loop at L2. Good. If DL is not 0, what are we going to do? If DL is not 0, okay, I better change this to conditional statements here. If DL does not equal to 0, go to L2. That's what this line is saying. And then these two lines combined, or these 3 lines combined, is saying what? What do you think? What am I comparing? I'm comparing CL with whatever EAX points to, but CL is loaded with whatever EBX is pointing to. So it's really comparing, whatever EAX points to with whatever EBX points to. And as a result of NZ, I'm going to label L1. What do I put here as the comparison operator? Not equal to. Yep, exactly. Okay. And there's one more line here, and what is this saying? If EAX is pointing to 0, go to L1 as well.
Shouldn't the first comment be if equal to, because you have to trump 0?
Say again?
Your first comment?
This one?
Up above that?
Oh yeah, it should be 0. So if
equal to?
Yep, equal to. We go to L2. Okay, there we go. And this is sort of EAX++. It's wrong because we're only increasing a byte. This is sort of EBX++. That one is really just DL minus minus. Okay, Whether it's pre or post doesn't really matter because nobody is really using the value of the expression. So I can use post or pre, increment or decrement. It wouldn't make any difference. Okay. And then the last line is just an unconditional go to L1 to L0. So we'll just put it here as well. Go to L0. There we go. All right, this is L1. L1 is comparing CL with EAX. And what is in CL? How can we get to L1? Okay, we can get to L1 because of this JNZ or because of this JZ. But regardless of which one we used to get to L1, CL has a value in it, right? CL already has whatever EBX points to in it. So we'll go ahead and just express that here. So if blah, blah, blah. Okay, so in this case, we are saying if whatever EAX points to is blah, 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 whatever EBX points to, go to L2. And what should I replace this blah, blah, blah with? It's equal because it's JZ to L2. So that means if these two are the same, we go to L2. And over here, we have the same comparison, but we are using a different comparison operator to represent this, because this is saying if EAX is greater than, if whatever EAX points to is greater than whatever EBX points to, go to L3, and then unconditionally branch to L4. Okay. Do we have a problem here? Okay, let's find out what is L2 doing. L2 is indicating the two strings are the same because we are moving 0 into EBX. L4 is indicating that the first string is greater than the second string because we're moving $1 into EBX. And L3 is saying the first string is less than the second string because we're moving a -1 into EBX. So the question is that the proper thing to do? How do we end up at L3? Which jump or conditional jump?
JA.
The JA to L3, right? But when you read the comment next to JA, that will do a branch if and only if whatever EAX points to is greater than whatever EBX points to. Would that be the right thing to do? It's opposite to what we want to do. Because when you scroll down a little bit more, it says EBX should be a 1 if str1 is greater than str2. But when you go back to how I initialized the pointers, str1 is initialized to EAX. So I got the sign flipped. Okay? Which means what? Which means, what is one test case that can reveal the problem? No. When string 1 is
Positive.
is greater than string 2, it will give you the wrong result. Okay? What if string 1 is less than string 2? Will it give us the wrong result? Okay, so go back to this code here and say, okay, but what if string 1 is actually less than string 2? If string 1 is less than string 2, this is not going to work, right? This is not going to go to L2 because they are not the same. The JZ is not going to branch. The JA is not going to branch because EAX is less than EBX, or whatever EAX points to is less than whatever EBX points to. So we have no choice but to go to L4. L4 is going to put a 1 into EBX, which also means it is going to be the wrong thing to do. So as long as you have two strings that are different, it will give you the wrong answer. Okay? So to answer the question, you go back to the original question here. The failing case is, you can use whatever example you want. The easiest one is when one is lowercase a and a null character. The other one is just a null character. because then the two strings are already different. So then you have to say, in that case, the exit code is supposed to be a 1, but instead it will exit with a value of -1. So that's basically what I'm looking for, is for you guys not only to spot what the problem is, but to give me a test case and indicate what is the correct answer for that test case, but instead what the program is actually going to do. Is that okay so far? But that's only one part of the question. The second part of the question is down here. Oh, I thought there's a second part to it.
It says fix the problems.
Okay. So find out which cases it will fail. So we got that. Reporting the wrong value and fix it. Okay, so we have to fix it by changing the labels. Okay, so you can fix it by changing the labels, or you can change the values that we put into EBX. So either way would work in that case. Note that some problems may not show up due to the addresses of str1 and str2. For those problems, catch them and fix them, but there's no need to document the failing cases. So for this part here, it is referring to how we increment the two registers. So instead of adding byte to AL, we should be adding long to EAX. Instead of adding byte to BL, we should be adding long to EBX. But those do not need to be documented because there's no easy way for you to control where str1 or str2 will be located. So you just have to say, okay, it's a problem, and we can fix those by these instructions, changes to those instructions. Is that okay so far? So that's the question number 3. That's the answer to question number 3. I think that's it for this particular test exam. String and compare. So that's the end of this one, but we have more. Okay, I know some of you want to have more exercise, so we'll go ahead and look at the other, practice exams that are already online. Store. There we go. So we just took a look at which one?
2014 fall.
Okay, so we can take a look at the 2013 spring. Oh, this one can just unzip. I have no idea where to unzip it to, so. Can't remember the name of the file. 2013. Okay, so here's another final exam, and this one has 6 questions, and I'm suspecting some of these questions have structures in it. So we'll go through each and every single one and figure out. Yeah, this one looks like it. Well, maybe not. All right, so this one is an easy one. I think this is why it has 6 questions instead of a fewer number of questions, because each one is relatively simple. So this one wants you to implement read num in assembly language. Okay, so read num is, okay, that's the prototype and the actual definition of read num. So how would you implement read num in assembly language? So let's take a look. Let's do a v-split and take a look at read num.s. Oh, it's already implemented. Delete, 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 delete. Okay. All right. So how would you implement this subroutine? First thing you want to do is to be able to access the parameters. Okay. Now, if you give me just a number like 8 EBP, I'm not going to mark you wrong. Okay. But as far as I'm concerned, it makes more sense to use a symbolic name, because if you give me a number and that number turns out to be wrong, I have no choice but to mark it down as completely wrong. On the other hand, if you give me a label, but the definition of the label is faulty, but the label name makes sense in the context, at least you can get partial credit for that. So that's why I think using symbolic name makes more sense. So I would just do the usual thing that I do. Old EBP is 0. Return address is old EBP plus 4. And then the first parameter is str is return address plus 4. And then the second parameter is pint is str plus 4, because each pointer is 32-bit long. Okay. Now that we have all of this stuff here, we have to specify the entry code and the exit code. Okay, because the only reason why EBP can be used as a frame pointer is because we change it using ESP. So we have to do the same thing as before. Okay. ESP to EBP, and then do the opposite when we exit the loop or exit the subroutine. So now that we have all the registers set up, we have one thing to do in the subroutine. We have to return the value of scanf. Okay. Some people will say, but we haven't really talked about scanf in this class.
But you
don't have to. It doesn't really matter what scanf does. Okay, it has absolutely no bearing to this particular question. All we need to know is it is passing pint, the parameter itself, as it is, and it's passing str as a parameter as it is. So the easiest way to implement this, there's nothing easier than this, is to push pint on the stack. But we're not going to push just pint as a label. We have to make sure that it is used in the based addressing mode, because we are pushing the actual parameter on the stack. And then we push the first parameter, which is string. Push this on the stack as well. Call scanf, whatever subroutine we're calling, we just use the call instruction. And I will take points off if people do not deallocate after the subroutine call, because otherwise, if you have something that is iterative in the loop, if you do not deallocate after this, the subroutine itself is not going to crash, but it will keep consuming space on the stack unnecessarily, which is bad. So I do want you guys to remember to deallocate. What about the return thingy? Do we have to specify anything?
It's already set to EAX.
It's already in EAX. So when scanf returns to this subroutine, scanf specifies the return value in EAX. You have to relay that to your own caller using EAX. So for those people who insist, okay, and say, I really want to do something when there's a return statement, you can do something like this. Fine. Because EAX contains the return value, and you will use it to specify your own return value. So that's why it is a move long EAX, which contains the actual return value from scanf into EAX, which is your return value to your own caller. But it doesn't really do anything. Is that okay? Okay, all right, so that's the first question. And let's move on to the second question. Second question obviously has to do with structs. We can skip that. And struct 2. This one is good. Looks like it's good. So we'll take a look at main.c first. Aha! Oh, this one is left. I like this one. This one has double, well, okay. It has dereferencing twice, and it has an increment somewhere in between. Okay? So the question is, how do you read the C code to understand what is going on and do it in assembly code?
You can flatten it if you want.
Sorry?
You can flatten it if you want to change it to assembly code.
Yep. Well, there's not a whole lot of flattening from the perspective of if, while, and stuff like that, because there's none of that. But the question is...
But that's kind of a complex statement you have inside your init inc.
Okay, so let's go ahead and implement this. hiding. Increment init ins. It's already done. Delete. Get rid of all this. Okay, start from scratch, right? Okay, first thing, usual stuff. OEBP is 0. Return address is OEBP plus 4. And we have one single parameter, which is PPI, which is pointer to an integer. That's why it's called PPI. Is return address plus 4. Okay, that's fairly easy. No local variables whatsoever, so that makes it a little bit easier. Push EBP, pop EBP, and then you have your move L ESP to EBP, move L EBP to ESP. Now we can specify the actual content of this subroutine. All right. What is the ordering of operation here? How do I know all the ordering of these operations? The right-hand side of the assignment is easy. Okay, it's just a 0. Okay, we can worry about that last. Okay, but the left-hand side seems like somewhat of a mess. Okay, but even if it's a big mess, how do you read an expression like that?
From inside the parentheses.
Yep, you go all the way into the innermost part of the parentheses. Now, in this case, there's no confusion whatsoever of the operator priority because I explicitly use parentheses to indicate do this first, then that, and then that. Okay? All right. So, what is the first thing that I do? What is innermost to the parentheses?
Dereference PPI.
Dereference PPI. Okay, so how do I dereference PPI? I need to get a hold of the parameter first, right? So move long, PPI, EBP. This is the actual parameter on the stack. I cannot dereference this. As much as I want to just put parentheses around this to say, hey, dereference that does not work. Dereference or indirect only works for registers. But that's okay. I can just put it into a register. EAX is good, okay? And then we can dereference it. So now we can dereference EAX and store the result back into EAX. It's okay to do that. So I want to comment what I'm doing here. So EAX actually gets the parameter itself, and now EAX is the dereference of that parameter. Are we doing okay so far with these concepts? Okay, so we are done with the innermost part of the left-hand side of the assignment. What is the next thing that we do to that?
Increment.
Okay, we do the post increment. In other words, we are attempting to, we are changing the integer pointed to, or we're changing the pointer pointed to by PPI first, well, second, but we want to use the pointer value before the increment for the next thing, okay? So, what does it mean, to us, at this point? What do we want to do?
You want to add L.
Okay.
You want to add 1 to EAX.
Okay. So maybe the dereference is a little bit premature. Okay. Putting the dereference into EAX is a little bit premature. Do you guys remember the technique that I used in class? How to deal with a post increment? I used push. Okay, so what am I pushing? So let's go back one step here. Okay, I have PPI. What am I pushing?
You're pushing what PPI? You're pushing PPI right now because you haven't dereferenced it.
Okay, what I need to push is something that I will be changing, right? What am I changing? Am I changing PPI? Or am I changing what PPI points to?
You're changing what PPI points to.
I'm changing whatever PPI points to. So what should I save on the stack? PPI or what PPI points to?
The second one.
Good one. The second one. Yes. How come it's always the second one? I have to change my instinctively. Okay.
Predictable.
Yeah. So too predictable. That's why I don't use multiple choice questions. Okay, so we are pushing not PPI, but what PPI points to on the stack. Okay, because we are going to use that for dereferencing later on. Okay, so we'll push that on the stack, and then what are we adding to what PPI points to. So this increment applies to whatever PPI points to. So I am going to add something to whatever PPI points to. Because EAX, remember, at this point, EAX is PPI. But the question is, what am I adding to whatever EAX or PPI points to?
4?
Well, that's an interesting question. It is 4 in this case, because what is PPI? What is the type of PPI?
It's a pointer to a pointer to an int.
It's a pointer to a 64-bit integer, 8-byte integer, okay? But that means dereference PPI to be of what type? Becomes a pointer to a 64-bit integer. Well, if it is a pointer, it's only 32-bit long, okay? So that means adding 4 is correct here. Oops. Okay, so this is not changing. Okay, so let me turn on line numbers. So line 14 is not changing the parameter itself; it's changing what the parameter points to. Okay, which is correct because in the C code we are also changing not PPI itself. We're changing what PPI points to by 4 bytes. Okay. Are there any questions at this point? So the side effect of the post increment is now done. Now we can pop whatever we push on the stack. Now we can push it back. We can pop it back to, let's say, EAX. Okay. But now I have to be careful because what does EAX contain at this point? When I do the push, I'm not pushing EAX while EAX is PPI. What am I pushing on the stack? Okay, let's comment here, okay? What am I pushing here? Save. Right? We're pushing what PPI points to on the stack before we increment it. So when we pop into EAX, what do we have in EAX at this point?
Start PPI.
Before the increment. Okay. In the C code, what are we doing with the entire inner expression? In other words, what are we doing to this whole thing? That's just this operator. What are we doing with that operator? Dereference, right? But what kind of a pointer are we dereferencing at this point? Are we dereferencing a pointer to a 64-bit integer, or are we dereferencing a pointer to a 64-bit integer?
By the time you get outside, it's just a pointer to a 64-bit integer.
It is a pointer to a 64-bit integer, so I am going to change a 64-bit integer to 0. Is that okay? Now that is significant because we don't have a single instruction to do it. The longest thing, the widest thing we can change with one single instruction is only 32-bit wide. So that means we have to put a 0 to whatever EAX points to, right? So we are basically saying whatever, okay, so this is what it's doing. It's, okay. But it's not entirely correct because we are only changing the least significant 32-bit of the 64-bit integer. We need one more instruction, 2 more instructions, one more instruction to finish this. How do we initialize the other 32-bit? With one single instruction. I know how to do it. It's easy to do it in 2, but how do we do it in 1? I just need one more instruction to initialize the most significant 64 bits of what EAX points to. We already know that addressing mode is just that, oh, we never use it in this type of context. What do we do? Move long, 0 to based addressing mode. The next 4 bytes. Is that okay or not? Sort of?
Isn't that
Need more time?
going to be moving 0 to what EAX is pointing to 4 bytes later?
But that's what we want to do because the first instruction is going to initialize the least significant 32-bit of what EAX points to. This initializes the most significant 32-bit of the 64-bit integer pointed to by EAX. Sort of, yes? Okay? Okay, but this is still a big mess. What do we do to something like this to make it easier to understand and visualize? I'm going to turn on the lights a little bit. Direction, here we go. Because I'm going to use the whiteboard, and you guys are encouraged to do something like this because it is helpful. What do you think I am about to do?
Draw memory.
Hmm?
Draw out memory.
Yep. Or mind meld, that might help too. Okay, so let's take a look at the original code in C++ first, figure out what it is actually doing. We have PPI as a parameter, okay? So as a parameter, it sits on the stack next to, in this call frame, okay? This is a part of the call frame, okay? So it's a call frame along with other things, okay? We know it is a pointer to an integer, which means this is 32-bit wide. It points to another thing that is also 32-bit wide, but this 32-bit thing, okay, so let's do the type thing here. So this is int 64 underscore t asterisk asterisk, which means it's a pointer to a 64-bit integer. This guy here is dereferenced once already, which makes this thing a 64-bit integer pointer, but not a pointer to a pointer anymore. But any pointer is 32-bit wide. But this one is a pointer, which means it also points to something else, but whatever it points to is now a 64-bit integer. Takes up 8 bytes. Is that okay? So is everybody okay with this picture? Without any operation in the subroutine, just based on the type of the parameter, the picture is like that. Where are these 4 bytes? I don't know. I don't really care. And these 8 bytes, somewhere else in memory, okay? They can be malloc, okay? Do you guys know what is malloc? M-A-L-L-O-C, memory allocation. Okay, for those of you who know C++, new. Okay, same thing. They can be dynamically allocated, they can be on the call frame of somebody else. I don't really care, okay? Now let's take a look at the actual operation in C++. The first thing we do is dereference. Okay? In other words, the first thing we do is we dereference to these 4 bytes. We never go back to PPI itself. We never really do anything to PPI except to dereference it. Okay? So we go to these 4 bytes, which is asterisk PPI. The auto increment, the post increment, applies to these 4 bytes. Okay? Which basically means we change these bytes to point to the next 64-bit integer. So I have to be careful because this is not the usual way I draw things, because I put higher addresses upper. So this is here. So we are changing this pointer to go point to the next item, the next 64-bit integer. So this change is the actual first change. First change is to change the pointer. But because this is a post-increment operation, the second operation, which is the dereference and the assignment operation, is not applied to the new 64-bit integer. It is applied to the first 64-bit integer. The 64-bit integer that was pointed to by PPI to begin with. So we are now saying, okay, the second operation is to put 32-bit zeros here. And then the second one is to put 32-bit zeros here. That's what we are trying to do. Is that okay? Just from the C perspective, this is not even referring to the assembly code, because we have to understand what the C code is doing first before we go try to implement this in assembly. Is that okay?
Can you explain again the part that is pointing to the
The next 64-bit? That's the plus plus. The post increment operator applies to the pointer pointed to by PPI. The pointer that is pointed to by PPI is this guy here. This is the one that gets the post increment operator. The post increment operator means the side effect is to change this to point to the next 64-bit integer. But the value of the expression is still the pointer that points to the original 64-bit integer. And that is what is getting the 0 because we are dereferencing the value of the expression. We are not dereferencing the value of the updated PPI. Okay? All right. So in assembly, what do we do? Well, when you look at these links here, it gives you an idea. Every time you have a pointing thing, it is a dereference. Okay, it's indirect. But we cannot do an indirect on anything other than a register. So that's why the first thing you have to do is to move PPI, EBP to a register first, because we cannot do an indirect on anything other than a register. So we need the address in a register before we dereference it. Okay. The next thing we do is to say, okay, this will get you to the address of this guy here. Not this guy, but the address of that guy. Okay? But the first thing we want to do is not to change it, because we have to save the value first, because we still want to get back to this location, the first 64-bit integer. We still want to get to it. So we cannot destroy it just yet. We have to save it first. So that's why the first instruction that we do, or after the move out instruction, is a push long instruction, and we are pushing whatever EAX points to on the stack. So we are saving these 4 bytes. We're copying these 4 bytes on the stack, which is a pointer pointing to the first 64-bit integer on the stack. Okay, so in terms of the picture, that means that here, somewhere on the stack, because this is a lower memory space, we have a copy pointer pointing to whatever PPI, whatever the pointer points that points. Whatever pointer pointed to by PPI is now saved on the stack. Is that okay? And then we can now go ahead. Now that it is saved, it is okay to change that pointer. So the next instruction is to do an add-on here. And we are only adding 4. This is wrong, because we should be adding 8 to it.
Is it 64-bit?
Yeah, because it's a 64-bit integer. So we should be adding 8, not 4, because we want this guy to point to the next thing here. So we are performing this operation. So the actual code is wrong. That should be an 8. Okay. All right. So that's the add long instruction, which completes the auto increment operation. So the plus plus is now done. I have done the side effect of the post increment operator. So what is left to do is to utilize whatever I saved on the stack earlier. Okay, so the next one is to pop L into EAX, which basically takes these 4 bytes on the stack and make EAX points to whatever these 4 bytes points to. So in the end, the result is EAX now points here, but these 4 bytes are no longer on the stack because of the pop instruction. But we do have EAX now pointing to the 64-bit integer originally pointed to by the pointer pointed to by PPI. Okay? And that is the one, because now we have the entire left-hand side, but what are we doing to the left-hand side? We want to change that 64-bit integer to 0. Is that okay? But how do we change a 64-bit integer to 0 when the widest move operation can only deal with 32-bit? Well, we can do it in 2 different instructions. Is that okay? So because EAX is pointing to the least significant byte of these 64 bytes, 64 bits, that means when we perform the first move out instruction, 0 into %EAX, which bytes are getting initialized? 0, 1, 2, 3. Okay, because EAX pointing to the entire 64-bit integer. Technically speaking, it really is pointing to the first byte of the 8 bytes. The first of the 8, right? So by doing this, we initialize the least significant 32 bits. But we still have the most significant 32-bit to initialize. And that's why we have the second instruction, moving a 0 to this time with a 4 outside of the parentheses EAX. But this is the base addressing mode, right? What does the base addressing mode do? It adds the displacement to the value of the register at runtime, and the sum becomes the actual address of the bytes being affected. Is that okay? EAX is still pointing here, but we add 4 to it, which makes it point to here. So these 4 bytes is now the recipient of the 32-bit 0.
So all you did was you took that chunk of code on the screen and
Yes.
graphically.
Yeah, but I'm doing it step by step as I point to the picture.
Okay.
Is that helping?
I typed it twice. I think this looks really familiar.
Yep.
I was under the impression that with base addressing, you weren't going to be dereferencing it at all.
With the base addressing mode?
Yeah, like with line
It is.
17.
It's really like indirect, except okay. If indirect is like going to that address, here's the address, go to that location. Base addressing mode is almost like that, except it is like, oh, here's an address, but don't go to the house at this address. Go to the next house, the house next to this, the one on this, at this address. That's what base addressing mode is. It's intentionally, offsetting where you're going, but it is in principle it is still indirect. The best way to understand how this relates to this one is the normal indirect is the same thing as having a 0 outside of the parentheses. Okay, so that's the best way to remember, because having a 0 here is really the same thing as just indirect itself. Okay. Would that help? Yeah. Okay, good. Are there any questions about this? Yep.
Do you prefer us to use the displacement, or can we use the?
You can use anything that would do the same thing. So if you prefer, you can delete, not use this, add 4 to EAX, and then have the same thing again. It would do the same thing. That would do exactly the same thing. Because the caller doesn't really care about EAX. Why? If you look at the prototype in C, why do you think the caller does not really care about EAX?
No return type.
There's no return value. The return type is a void. So from the perspective of the caller, which is down here, whatever EAX is, doesn't really matter. The caller does not pay attention to EAX after the call. So you can put whatever you want into EAX, it doesn't do anything. Are there any questions about this point? No questions? Okay. If there are no questions about this one, we'll go to the next one, Q5. Q5 is string n compare. Okay, that looks familiar to us. Okay, so this one is a real string compare, and I want you to do it in assembly. Okay, so that would be this part here. How do we implement this all in assembly? I think we have done this, or at least we have done string compare itself in class. So this wouldn't be too big of a jump here. Okay, let's do it. Go ahead and do it anyway. All right, so we'll do a B split, and on the right hand side we'll do the assembly code. Okay, my string and compare. Okay, Okay, first of all, all the usual stuff, boring stuff. Okay, so we have OEBP being 0. Return address is OEBP +4. The first parameter is str1, is return address +4. str2 is str1 +4. And then n is str2 +4. Okay, so we have all the usual label stuff done. Then we have the entry code, the exit code. So for those of you who usually cannot remember the entire exit code and entry code, you can just put it on a piece of paper, bring it with you, because this is going to be useful. Okay, so move ESP to EBP, move EBP to ESP. But don't just memorize the sequence of instructions. You have to understand what each instruction is doing and why it is useful. Okay, so having a piece of paper to remind you what those instructions are is good, but understanding it is just as, if not more important. Okay, so now we got everything set up. We just have to implement the subroutine. This is a while loop, so we have a while begin, a unconditional branch back to while begin, and a label to indicate the end of the while loop. So inside the while loop, we have to first evaluate the condition, which in this case has 3 components. Okay, so we have to evaluate all 3 components. But you have to specify the exit condition instead of the stay in loop condition. The exit condition of conjunction is easy because it's a disjunction of all the negations of the expressions. So in other words, instead of saying, oh, n has to be non-zero to stay in the loop, you just say, when n gets to 0, it's time to get out. Instead of saying, whatever string 1 points to has to be the same as whatever string 2 points to stay in the loop, you just say if they're different, time to get out of the loop. Instead of saying whatever string 1 points to has to be a non-zero, you just say when it gets to 0, it's time to get out. So it is actually easier to deal with conjunction in the while condition than a disjunction, because a disjunction has to turn into a conjunction. And conjunctions are a little bit harder to deal with. Okay, first thing first, we have to look at n and do something about it. Compare n to something. It is just implicit that we're comparing it to 0. Okay, and EBP. And if it is 0, we get out. So we go to while end. That's the first part of the conjunction in the loop. The second one has to compare whatever str1 points to whatever str2 points to. But then you have to be careful because you have to remember what str1 is pointing to. Is it pointing to an integer or is it pointing to a character? Because that determines the width of the compare. And the other thing is they are both in memory. We cannot do it in a single comparison. So you have to move one of them into a register first. So you have to move whatever str2 points to. Well, you can pick the other one too. Doesn't really matter which one. So you have to move it into a register. I can use AL here. And then you compare byte. Okay, make sure that you're using byte operation in this case to whatever str1. Ooh, I cannot do that, can't I? I just made a mistake here, big mistake. Because I'm supposed to do what? Dereferencing. I forgot to dereference. So I have to move the entire parameter into a 32-bit register and move the other one into another 32-bit register. Okay, there we go. And then we can do the move byte instruction, indirect EBX to a 8-bit register. So we have to pick, I don't want to use B, I want to use C, because B is kind of special because EBX has to be saved and restored by the subroutine. So if I don't have to do it, I don't want to do it. And then we have a compare byte instruction, DL to whatever EAX points to. Okay. And to stay in the loop, they have to be the same, which means if they are different, we are getting out of the loop, like that. So that will handle the second part of the conjunction. Now we have to handle the third part. The third part is not bad because we have str1 already in one of the registers, which is EAX. So what is left to do is just to compare byte. Yeah, okay, we'll do it the same way as what the code is asking for. So we'll just compare whatever EAX points to 0. And to stay in the loop, it has to be non-zero, which means if it is 0, we get out of the loop. So now we have the condition of the while loop handled, and we are now into the body of the loop. Are there any questions before we get into the conditional statement in the loop itself? It's all good? Okay. All right. So the conditional statement also has a template, because in this case it does not have an else, but we will still need an and-if label in order to identify, hey, the condition is false, we don't want to go to the then branch. Okay, now we have to specify the condition. The condition is minus and itself, which is easier to implement compared to post decrement, because this is just saying, oh, let's do the operation first, subtract 1 from and then use the value of n to do something. Okay, so I just spelled out the operation. Subtract 1 from n is a 32-bit integer, so we use subtract long from n. And then we compare n to 0, okay, CMPL. Now we don't really need to do that because the subtract instruction will automatically set the z flag if n gets down to 0. So the compare to 0 is redundant. Are we doing okay so far with that concept? There's no need to do it, but if you want to, comparing to 0 is okay. But I'm not going to do the compare to 0 just to show you, you do not need to do that. The C code is basically saying after the decrement, if n is non-zero, we go to the then branch, which means if it is 0, we we branch around the then branch to end if. And now here we have the actual then branch. The then branch is fairly easy. We're just adding 1 to string 1 and adding 1 to string 2. So I'm just going to add 1 to str1 EBP and adding 1 to str2 EBP. So I am not relying on registers to remember the parameters, because this way, I don't have to track all of that stuff in my mind. I can just say, okay, they're all done the same way as in the original C code. Okay, I'm done with the conditional statement. I'm done with the loop. Now it is time to specify the return value. Now the return value is a nested ternary operator or ternary expression. When you have nested ternary operation, the second one is nested as the else of the first one. Okay. In other words, in the C code, if you have any questions about operator priority in the test, you can just come ask me. Okay, because this is a assembly language class, not a C class. So if you have questions about these simple things, it's not a big deal. Okay, so getting back to here, how do I implement this?
So you're going to look at the value of string 1 and compare it to the value of string 2.
Yep. All right. Can I count on EAX and ECX being initialized at this point? That's a trick question.
I would replant them into register.
I cannot count on it because the loop could have exited because of n being 0. So in that case, EAX and ECX may not have everything initialized. So what I would do is just to do the initialization here again. Okay, put str2 into ECX, move str1 into EAX. So now I don't have to keep loading those things again and again. Move byte ECX into register DL, and then do one single compare DL to EAX, indirect EAX. All right, but that's all I need to do, because now I can perform, based on one single compare, I can figure out all of these answers. Because in C++, it looks like I need 2 comparisons to get to the 3 possible results. But in assembly, one single compare will set all the flags that you need to know to know where to branch. So one single compare is really all you need, but the difficult part is to specify, okay, but how do I control the branching? Okay, the first condition is a -1, which is when whatever EAX points to is less than whatever the other one is pointing to. And here comes the question. I know this is a jump conditional branch instruction, and it says not less than, okay? But if I want to specify not less than, should I use JNL or JNB? Not less than or not below? In other words, what is the sign, is char signed or not? Is char signed?
Char is unsigned.
Char is signed.
What?
Yeah, it is signed. So you have to use JNL in this case to not -1. Okay, I will show you why, how I know that. Okay, it's very easy to run an experiment for that. Okay, JMP to and subroutine. Okay, so if it is less than, we want to move -1 into EAX as my return value. If it's not less than, I still have one conditional branch here, because if it is not equal to, then we want to say positive. And positive is here. And this one will jump around the other code. And if it is positive, we want to move a 1 into EAX. And positive, oops, I made a mistake here. Okay, this is intended to be a 0. Nope, that's correct. That's okay. And here we want a positive 1. There we go. Okay. Just quickly go over this. J and Z means if they're not equal to, right? Well, how do we know not equal to automatically means it's positive? Because we know it's not negative already, right? If it's not negative and it's not equal to, it has to be positive. So that's why we go to positive if it's not equal to. So the only way to get to here is it is not less than, yet it is equal to. Well, equal to means we just need to put a 0 into EAX as the result. So that's how this code works. Okay, let's go to the question of whether a character is signed or not. Okay, I can go to GDB and know the answer right away. How can I do that?
You can print a hexadecimal number as a character.
Yeah, we can do that. So we can cast a particular value as a character to see whether char is signed or not. So what bit pattern would be good to use here? Well, let's try some of the ones that we kind of know already. Okay, 20 is the space character, right? Press the enter key and it displays, it's 32 and it's also the space. Not very helpful. So what do you think would be a good one to specify as a bit pattern so that we can see whether char is signed or not? FF is a good one, sure. Okay, because anything that has the most significant bit set would be a good one to use. So FF is a good one. It prints -1. Oh, but what if this is a bug in GDB and it's maybe we can see if we can print unsigned char, because if I cast FF to unsigned char to be very explicit that we want the unsigned interpretation, what should we be getting? What should we be getting in this case?
Well, now it should be different because...
It should be different because, well, it's the interpretation, right? It's the value represented by the same bit pattern that is different. So if I cast this explicitly to unsigned char, what do you think is the value represented by 11111111? 255, right? 255. And that's what we get. So this is how I know pretty much right away that char is signed. And all without G++ or GCC. because GDB understands types.
I guess I just think it's a little weird because
It is weird.
It's
I
relying on an
know.
ASCII table, so it just makes sense to be unsigned.
Yep, I know. That's what I thought too, but experiments proved otherwise. Question number 6. Array of structure, can't do that. And I think that's it. Number 6 questions. So, any questions? Anything else you guys want to ask? Clarify? Want me to demonstrate? You mean for this homework? I can do that. Well, I don't have it yet, but I can. Do you guys want me to work on it now? I mean, that's cool too. You're kind of tired. You are tired. Okay. Well, I can. Yeah. Go ahead.
The other assignments that we submitted that have no grade or not graded yet.
They will be graded. But what about the last homework assignment? Do you guys want to kind of have me to take a quick jab at it?
Sure.
Okay, jab. I need a dagger for that, not a long sword. Alrighty, let's take a look at the homework assignment. It is in subroutines. Interface with C. String D copy. Probably have it already sitting somewhere. Yeah. Okay, there we go. We already have it. So we'll go ahead and open up both the C code and the assembly code side by side. There we go. Oh. There we go. Assembly code, C code. Alright, same thing. First thing is to define all the labels. So, boring stuff. And then we have destination as the first parameter. Source as second. And delim as third. There we go. We have one local variable, which is kind of not necessary because if you just do a push and a pop later on, it would do just fine. But since I want to be truthful to the C code, we'll go ahead and do it that way. O destination is my local variable. It is sitting on the other side of OEBP, so it's OEBP -4. Entry code, push EBP, move ESP to EBP. Exit code, do the reverse, move ESP to EBP. Okay, do you guys have any questions? No? Okay, alright. Pop L to EBP, like so. And don't forget to allocate for the local variable, because otherwise, we step on the bug, the one thing that we talked about today. So we want to add long, in this case, since we only have one single local variable, so we just add it to the stack pointer. Because it's already a negative value, this is allocating more space. Okay, do you guys have any questions? Because if I can hear you, other people can hear you as well. Okay, thank you. All right. So the first thing we want to do is to save the current value of destination into old destination. Instead of doing things the really boring old way, I'm going to try some new ways of doing things. Okay, so I'm going to try this. Okay, so we're going to push dest, which is the parameter on the stack, and then when I pop, I don't pop it into a register. I pop it into old destination EBP. It will do the same thing. In fact, this is actually the lengthier way of doing things. This will take longer compared to copying to a register first, but it looks cool. All right, so that takes care of the initialization of old dest, and now we have the rest of the loop to deal with. So as usual, I mark the beginning of a loop, mark the end of a loop, perform an unconditional branch at the very end to the beginning, and then we specify the condition. This way, if I do things this way, I will not forget the unconditional branch all the way at the end. If I do it, like sequentially, sometimes I would forget the branch back to the beginning. So instead of having a while loop, I end up having a if statement, which is not good. Okay. So now that we have a while loop, the first condition is to see if whatever source points to is null or not. Okay, so let's do that. So we move source EBP into a register, and then we just compare byte, okay, not long because source is a char pointer. So we compare 0 to whatever EAX points to. If it is 0, time to get out. Because we want to stay in the loop if it is not 0. Then the next thing we do is to call the subroutine string char, and then do something about the return value. I'm not too worried about the negation first because I need to call the subroutine first. The first thing we need to push is source, which is a character. But we also learned that the compiler always push 32-bit. In other words, it always pushes a integer on the stack. So to be safe, this is what I would do, is I am going to move, I'm going to do it this way. So I'll move a 0 into EAX as a 32-bit register, and then, I cannot do that. Well, I can use ECX. And then I'll move byte from EAX to CL. In other words, I'm initializing the whole thing here. It's still not the right way to do it because sign extension is still not done correctly this way. But for this, it'll still be okay. Okay, so this is supposed to be okay because only the least significant byte is actually used. So, there's no need to do it because the address is already in EAX. So I can just do a push long indirect EAX. That will push the byte that I want on the stack along with 3 additional bytes. Okay. So that's the second parameter. The first parameter is just itself. So it's just dlim EBP, which is a pointer. Push it on the stack. Now it is time to call the subroutine. So just call strchr. When it returns, the first thing we do is we adjust the stack pointer to reclaim the 8 bytes for the registers, for the parameters. Then we have to decide what to do with EAX because EAX contains the return value from string char. String char returns a null pointer if the character, which is the second parameter, cannot be found in the null terminated string, which is our first parameter. Otherwise, it returns the pointer, a non-zero, non-null pointer to the character in the lim. But as far as we are concerned, we just need to know whether it's a null pointer or not. If it is not a null pointer, we stay in the loop, which means if it is a null pointer, we exit. So that means we have to compare EAX with 0. If it is 0, it is time to get out of the loop. Is that okay? Yep.
Do you push EAX into the stack?
Push EAX indirect. Yes.
Indirect to the stack. For sure, the function that you call will know that the last byte is what it's going to use.
Not the last, the first actually.
The first.
The least significant byte. Yes, it does, because the type of the parameter is actually, actually it is an int, but the if you read the function description, it knows that only the least significant 8 bits should be used. Yeah.
Shouldn't it be jump if it's not 0?
Sorry?
Shouldn't it be jump if it's not 0 to while n?
Oh, you're right. Yep. Because if it is 0, we stay in the loop. If it is non-zero, we get out of the loop. Thank you. Very good. Okay, in the loop, we have to first do the copy, and then we increment the pointer. So even though on each side it is a post increment, and it seems like we have to do all the crazy stuff that we did earlier today, it's okay not to do it that way because we can just do it, the other way. At this point, we know that EAX has the EAX cannot be relied on, so we have to copy all the pointers back into the registers and then do the copying. So we have to move source into EAX, move destination into ECX, do a move byte, indirect EAX, which is the source, into CDL, move byte from DL to indirect ECX, which is the destination. And then we can just go ahead and increment both pointers. So we say add L $1 E source, add L $1 destination. So that takes care of the inside of the while loop. When we get out of the while loop, the only thing left to do is to put a 0 to whatever destination points to. The post increment is okay. You don't have to do the post increment because nobody really cares about the value of destination after this. So it's okay not to do the increment. So we need to do a move L destination to E. Well, I'll just be consistent and use ECX here. Move byte 0 into indirect ECX. And now we are down to the return statement. So the return statement is just moving old DEST, which is our local variable that saved the original value of destination. And we just have to copy that to EAX. And that should be it. So I claim. But do you guys think this is correct? Aha, very good. Okay, you should apply that reasoning to every single class that you take. Do not take my words for it. Or any professors for that matter. Alright, so we'll go ahead and make. And it complains as okay, typo. 34, add long. Okay, there we go. Make again. So I'm feeling kind of brave right now, so I'm just going to run the program by itself. Okay. Okay, seems to work okay. Okay, tricky cases. Okay, so let's take a look at some tricky cases here. What do you think would be a tricky case? We look at the C code first, and then we say, okay, what do you think would be a good one to trip the program? Try to trip the program.
You could have a tab first, or
Okay, a space or a tab as the first character, right? Then it should output what? Well, a null string, which is empty string, right? Okay, so let's go ahead and do that. Okay, so we'll run the program, specify a space, and that's the first string. Press the enter key. Now, how can you tell whether it is printing a space or is printing nothing on the second line? You cannot tell, right? So what do we do to test it, to make sure that it is actually an empty line that it is outputting? Okay, so we specify a test file with a single space. We double check that the input file is in fact a single space, okay? And a line feed character, because we need the line feed character to convince the string reading mechanism to end, okay? And when we run the program, we redirect from test1.in, and then we redirect the output into a file. Then we can go back and examine the file using Hex Dump, because if you print it out, you cannot see. But when you do a Hex Dump, you can tell whether it is containing characters or not. So now we can do a Hex Dump, not on the input, but the output file that we just collected. It has a single line feed character, which means it is in fact an empty string. Is that okay? All right. Any other tricky test cases?
I'm trying to tab too, just to see if it is.
Tab, okay, we can try a tab. So we'll go ahead and specify that in another test file. Okay, in this case we have a tab. So to specify a tab, it is Control V, Control I, or just, I think Yeah, Control E, Control I is the best way to do it in VI. So now we specify the same thing, except it's test2, and we collect it into the test2.out file, and then we run the program. We ran the program already. It's time to just examine the output, and it is also empty, which is correct. Here comes another question. What if I specify a null character on its own in the input file? What do you think is going to happen? Okay, first question. How do we make a file that has a single null character and a line feed character? I think we kind of talked about that in this class.
Control something.
Control something. Very good. Okay.
Control V.
Control V and then Control at
Yeah, there you
in VI, but in Pico, I'm not really sure how to do that. Okay. Yes, you are. So we copy test2.in to test3.in, test3.in. We replace the, we remove the tab character, and then we specify Control V and then Control at. Okay, you cannot really see it, but in very faintly, in dark blue, is a caret and then the at sign. Okay, that's okay. Well, we can see it now. Okay, but when we do a hex dump, it will be really clear. So hex dump test3.in shows you exactly what it has. It has a byte that is the null byte and then a line feed character. Is that okay? Now, when you read the main program uses fgetS to read in the string. So the question is, what do you think is going to be in fget, the result of fgetS? It's going to be, okay, let's try to read the documentation on fgetS and see if the null character has any special meaning to fgetS. So man fgetS, okay, input of char strings, okay, read the description, reads in at most one less than size characters from stream and store them into buffer pointed to by s. Reading stops after an EOF, okay, so we don't have an issue with EOF just yet, or a line feed. Is the null byte specified here to control when it stops?
A terminating null byte.
Ah, but this is after. It is stored after the last character, which is the line feed character. So this, in fact, will read a null byte, the line feed character, and then it will append another null byte at the end of that. Okay? But as far as we are concerned, there's only one single null byte in this particular program. Okay? But will the C code work correctly? In other words, if you look at string D copy C, what is this code going to work? Because your code is supposed to mirror this code. Okay? So the question is this going to copy anything? Okay, this is actually a pretty easy way to analyze, because the first byte that the source is pointing to is null. Okay? It is null to begin with. So that means this condition is false to begin with, which also means we do not even enter the loop once. Okay? We skipped all of this stuff here, but it doesn't mean destination doesn't get anything, because this is after the loop. So the destination, the first byte of the destination, gets a null character. So in the end, we still end up with an empty string. It is an empty string, which makes sense, but it is initialized. The most important point is it is initialized, and we should not get gibberish as a destination. Is that okay? How do we know this is actually the behavior of this program? Well, we test it out, right? So we say main redirect in from test3. Is it 3 or 4? 3. Okay. Redirect out to test3.out. Hex dump -c test3.out. It is just an empty file. Okay. Well, it's an empty line. The single line feed is just to separate this line from the next. What about the other funny characters? I mean, anything that we did not mark as a delimiter should stay in the string, right? And one of those things that is kind of strange and doesn't seem to make a whole lot of sense is the return character. Okay, the carriage return character is not the same as a line feed. This is because of typewriters. Okay, does anyone have a real old full manual typewriter that does not have a cord to plug into the electrical outlet? Nobody?
My sister does.
Okay.
That's my experience.
Those things are great. They're very tactile. Okay. In fact, after typing a long English paper, your hands will sore. Definitely you will feel it. Okay. But the question I bring that up, the reason why I bring that up is because line feed is just rolling the drum so that you move on to the next line. Carriage return is actually moving the entire roller back to the home position. So those are two separate mechanical actions on a full manual typewriter. So that's why carriage return is different. And we never specify carriage return as a delimiter because it's \r, and if you look at main.c, \r is not on the list. Okay? So that means if I create another test file, this would be test4.in, and specify the carriage return character. So the carriage return character is Control V, and then A, B, C, D, E, F, G, H, I, J, K, L, M. Okay, Control M. Oops. Control V, Control M. Oh, it doesn't let me specify that. Great. Okay, Control V, Control V, Control M. There we go. Okay. So here's Control M. We'll double check using Hex Dump. Hex Dump -C test4.in. It is 0D. 0D is 13, which is the ASCII code of the carriage return character. Okay. So we do have everything in place. Time to run the program. Capture the output. Do a hex dump on the output, because with all of these, it will be pretty hard to see from just the output. So you have to use a hex dump to actually examine the output, and it is output, which is correct because it is not a delimiter as far as this program is concerned. So, are there any questions about this? Questions? Alrighty. So I'm going to upload all the video stuff and whatnot, and I'll see you guys next Tuesday.
In the morning.
Have a nice weekend. I felt like RoboCop. In RoboCop, the police vehicles all have a nice day, as a label.
Oh, they really have quotation.
Yeah. Well, they don't need the actual quotation.